start recording now. So yeah, so today we will start looking at energy balances and CO2 emissions. And I will just start sharing my screen for the presentation. Yeah, so the session today is on energy statistics and energy balances. As you know, energy statistics is very important, but you can really add value to your data by creating energy balances. And then once you have your energy balances, you can move even further and use that information to calculate CO2 emissions from fuel combustion. So the agenda today, so we are doing the third webinar, which is on energy balances and CO2 emissions. And then we will meet again on Tuesday. So on Monday, we don't have a session. So on Tuesday morning, we will look at energy prices and taxes and energy efficiency indicators. And that will close the first part of the statistics module. And then we will start with the modeling on Wednesday. Again, some quick housekeeping rules. Now, I guess you're getting used to this slide. So this whole session, it's on virtual and we are recording it to put on YouTube after. If you have any urgent, important clarification, you can raise your hand and we will stop the presentation and answer to you. But otherwise, please use the question and answer box to write down whenever you have questions. And during the balances presentation, I will be joined by Alex, who is an expert on energy balances like me, and we will both answer your questions on energy balances. And then on CO2 emissions, I will be joined by Puya, who is an expert on CO2 emissions calculation. Again, if you have any other questions, you can drop an email to me, to Arnaud, or to the email of the Africa program. So the energy balance, it's a natural starting point to study the evolution of the domestic energy market, to forecast energy demand, monitor the impacts of energy policies, and assess the potentials areas for action. And this presentation today, it will be divided into 5 parts. First, we will look at what is an energy balance, how it differs from the commodity balances that you have looked yesterday, and how at the IEA we construct those energy balances. Then we will see the importance of calculating an energy balance and the different advantages you can derive from it, such as generating indicators for analysis and for CO2 estimations. Then we will also study the principles of creating an energy balance. We will look at the IEA methodology and also the definitions used with a focus again on calorific values. I will then show you how the IEA energy balance looks like and how the transformation of energy happens within the balance. And finally, we will see how with the data from energy balances, we can calculate CO2 emissions from fuel combustion. So let's get started. So what is an energy balance? The energy balance, it's a representation of the basic supply and demand data for all fuels in a manner which shows the main fuels together, but separately distinguished and expressed in a common energy unit. So the energy balance, it takes the form of a matrix where the columns, it represent the different energy sources, so the products, categories, and the rows, it represent all the different flows that are grouped into 3 main blocks. So you have the supply block, you have the demand block, which is separated into the transformation and the final uses. So To develop an energy balance from the set of commodity balances, there are two main steps. First, you have to convert all the data to a common energy unit. So at the IEA, we use the ton of oil equivalent. And this allows us to compute the total column. Given that you're reporting all your products in the same energy unit, you're able to calculate your total column. And also there are some reformatting that is performed in order to avoid double counting when you're summing all products together. This format of energy balance, it allows us to make an easy comparison of the contribution of each fuels in the economy. And also we can see the interactions to the conversion of one fuel into another. So again here, so with the energy balance, you can have the global picture of the energy situation of a country. Another way to present an energy balance, it's through the Sankey flow, which is a graphic format. So before we had a tabular format, and this is a graphic format, and it is exactly the reverse matrix with the products and flows. And this, the Sankey flow, it allows you to have a very quick visual picture of the energy sector of the country over time. The arrows here, so for example, in the slide here, you can see the Sankey flow for Africa. And in the arrows here, you can see on your left side, the energy flows from production to the right side to the final consumption. So you can see that flows can be combined, splitted, and traced through a series of events. The width of the arrow, so for example, here, the width of oil product, it shows you that it gives you an indication of the flow quantity. So it's proportional to the flow quantity. And also when I really recommend you to connect to the IEA website. You have the link here, and browse through the different Sankey flows for your country or for your other countries. And you can use the timeline also to show how the energy balance has evolved over time. So you can really show from 1971 to now. So the latest data would be 2018-19, how a product has evolved, how a sector has evolved. This is the Zambia Sankey flow. So here again, just with a quick glance, you can see that biofuels and waste is the main energy commodity used in the country. It's the first commodity that is produced. You have a bit of oil and oil products imports. You have a little bit of coal product production, and some hydro production as well. And then if you look at the final consumption on the right, you can see that most of these biofuels, it's consumed in other sector, which is residential and services. And then some of it also goes into industry. And most of the oil, it goes into transport and a bit into industry. So let's do some interactive questions again. I will connect to the Sankey as well. So please connect yourself to the www.menti.com and use the code 30, 83, 94, and 20. You can see the code here, 30, 83, 94, and 20. And the first question is it possible to have a statistical difference which is equal to 0 in a statistics table, which is in physical units, and a non-zero in the related energy balance? So think about it. Is it possible to have a statistical difference which is 0 in a statistics table, and which is not 0 in the related energy balance? So we have 8 people who have answered, and half of you think now more thinks that yes, this is possible. It's half-half. I give you a bit more time to think about it. If, for example, you have your data for coal in tons and there's no statistical difference, and then when you create your energy balance in TOE or terajoule, whatever units you use, energy units you want to use, is it possible that then in the energy balance, you end up with a statistical difference? So we have 19 people, 20 who have replied. And the views are quite similar between yes and no. Now more and more think yes. And the correct answer is yes. So yes, it is possible because of many reasons which we will see in the presentation, and one of them is calorific values. If you don't report proper calorific values, you can end up with a statistical difference in energy units, even though in physical units there was not, there was a zero statistical difference. The second question is, in an energy balance, you see a positive number in the total column of a transformation flow. Is it possible? So I don't know if you can visualize in your head an energy balance. So you have the different products in the column. And then, for example, I'll give you the example of the refinery transformation. So you have your crude oil that enters your refinery. So that amount of crude oil will be shown as a negative number in the refinery row. And then you have oil products that are produced, and that oil products production, it will also appear in the refinery row as a positive number. And then your total column, which is the sum of the rows, it's either positive or negative. And here we are asking the question, is it possible to have a positive number in the column of a transformation flow? If you think yes, because this means that the transformation efficiency is very high. No, transformation output are always equal to input and totals are always equal to 0, or no, totals are always negative because transformation efficiencies are always lower than 100. So maybe think about what I just gave as an example. You have an input of crude oil, which is a negative number. You have an output of oil products, which is a positive number. And when you sum the two, that is what will appear in your total column. And this number, can it be positive? In the meantime, while you answer, so someone asks for the code. The code is 30839420. So yes, we have 26 participants who have replied, and 17 think that no, it is not possible because totals are always negative, because transformation efficiencies are always lower than 100. And this is the right answer because in energy terms, you cannot produce more than what you're inputting. But in physical terms, this could have been possible, for example, in a refinery that you put, for example, 100 kiloton of crude oil, and you get 105 kiloton of oil products. So this is possible in physical terms. But in energy terms, this is not possible. You cannot produce more energy. So this question, we'll keep it for when we do CO2 emissions. Now I will go back to the presentation. So yes, and then I will share this one. Now, let us see in more details the importance of calculating an energy balance and what you can derive from it, such as generating indicators for analysis and CO2 estimations. The energy balance is a way of reporting energy data in a common unit and with products aggregated by category. It has many benefits and uses. By presenting all the data in a common energy unit, the energy balance allows users to see the total amount of energy used and the relative contribution of each different source for the whole economy and for each individual consumption. It also allows comparison of the shares of each source in the energy supply of a country and in each sector of economic activity. Different countries can be compared when they are calculated with the same methodology. With an energy balance, you can develop various aggregated indicators such as consumption per capita or per unit of GDP, and to estimate CO2 emissions from fuel combustion. A country can determine its dependence on energy imports or exports. With an energy balance, it is possible to analyze energy efficiency. The statistician also uses the energy balance as a high-level check on the data accuracy, as large statistical differences in energy units, apparent energy gains, or large losses in transformation processes may all indicate underlying data problems. Also, it allows us to have a good basis for making forecasts and projections to achieve climate goals and to check that policies in place are well implemented. If you want to exploit the full potential of an energy balance, it is recommended to combine energy statistics with economic indicators. These new aggregated indicators allow us to understand how energy impacts society and economy. For example, we can calculate the energy intensity and self-sufficiency of a country. Energy intensity is a measure that is often used to assess the energy efficiency of a particular economy. The numerical value is traditionally calculated by taking the ratio of energy supply to gross domestic product, indicating how well the economy converts energy into monetary output. The figure on the left side shows us how primary energy use and GDP have changed globally over time relative to a normalized year of 1990. As you can see, GDP and total energy supply are decoupling, and this can be due to several reasons such as structural changes and efficiency improvement. In sub-Saharan Africa, the energy intensity is decoupling less quickly than globally. Obviously, low energy intensity is the desired goal because it represents an efficient allocation of energy resources to generate wealth and a high quality of life. So it is logical to expect energy intensity to increase and for GDP and energy use to be closely coupled during the initial stages of development of a nation, since the early years of access to electricity and utilization of more abundant energy includes many energy-intensive activities. The developing economies will need to produce a tremendous amount of cement for roads and buildings, as well as steel for automobiles, appliances, and telecommunication infrastructures. These will be new uses, some of which will naturally be energy intensive.
We can also compare countries to see where each other stands for. In this graph on the right side, you can see that OECD countries are less energy intensive compared to non-OECD countries for the reasons I mentioned before. In sub-Saharan Africa, the differences between countries are quite large. Some countries, such as Democratic Republic of Congo, is more energy intensive compared to Ghana. Another indicator is self-sufficiency. The energy self-sufficiency rate is the ratio between national primary energy output and consumption of primary energy in a given year. This rate may be calculated for each energy types or overall for all types of energy. A rate of over 100% indicates a national production surplus in relation to domestic demand and therefore net exports. For Africa, if you remove biofuels from the energy mix, then the self-sufficiency declines a lot. In sub-Saharan Africa, a very high self-sufficiency rate is due to the top oil producers. Now, if we compare the self-sufficiency by country, we see that again there are differences because of biofuels and waste. For example, for Uganda, the self-sufficiency can seem very high at around 90%. But if we look at the energy balances, we see that there is a very high share of traditional biomass in the energy mix. And if not accounted, we see self-sufficiency drastically decreasing to 16%. Conversely, for Nigeria, who is a strong oil producer, self-sufficiency even increased because most of the oil is exported and biofuels consumed domestically. However, concerns for oil producers in Africa are on the midstream infrastructures, namely refinery, and countries will indeed import most of the finished products beside a large national oil production. In the case of Ethiopia, if we remove biofuels from the self-sufficiency, then Ethiopia is producing only 20% of its energy demand. Another indicator is the residential consumption per capita. So how much are we consuming at home? In this chart, we can see that the difference between OECD countries and sub-Saharan Africa is quite large. In sub-Saharan Africa, we consume 50% less energy in residential sector compared to OECD countries. However, traditional biofuels used in sub-Saharan Africa is quite large and inefficient, and the useful energy consumed per capita is much lower. This is how the picture looks like if we exclude solid biofuel consumption, which is very inefficient consumption per capita in sub-Saharan Africa. We see that the gap with the OECD is even higher and consumption per capita is very low. Now, let us look at the methodological assumption underlying energy balances. As you know, energy data are generally collected independently across different commodities. To develop an energy balance from the set of commodity balances, there are two main steps. The first one is to convert the natural units in the different commodity balances, that is for coal, oil, gas, renewables, and electricity, to the chosen energy unit. Here it is kiloton of oil equivalent in the IEA balances, but many countries use terajoules. by multiplying by the appropriate conversion equivalent for each natural units, which are calorific values. The second step is some format changes. We need to do some reformatting in order to avoid double counting when summing all products. We need to rearrange the converted commodity balances along one another, rearrange certain of the rows, and introduce a sign convention in the transformation sector. What is a calorific value? It is the amount of heat obtained from one unit of the fuel, and it is the only way to convert a fuel quantity from natural units, that is mass or volume, into energy units, that is kTOE. It is very important to collect good quality calorific values in addition to good data in physical units. As you can see, in this commodity balance, there is no statistical difference. But when we convert to the energy balances using calorific values, then a statistical difference appears. Why? If we look carefully at the calorific values in the middle table, you will notice that the calorific value for the input to electricity and consumption is different from the production and imports. This is something to query with the country. So as you can see, calorific values can be a good check for data quality control. Now, let us look into more details at the principles of an energy balance. The main methodological choices underlying energy balances that can differentiate the final balances layout across organization are as follows. The IEA energy balance methodology is based on a common unit of account and on the calorific content of the energy commodities. The IEA balances are expressed in terms of net calorific value. The change from the original units to tons of oil equivalent implies choosing coefficients of equivalence between different forms and sources of energy. When constructing an energy balance, it is necessary to adopt conventions for primary energy from several sources, such as nuclear, geothermal, solar, hydro, wind, etc. For each of these sources, there is a need to define the form of primary energy to be considered. There are essentially two methods that can be used to calculate the primary energy equivalent of these sources: the physical energy content method or the partial substitution method. Also, temperature adjustments made by countries should also be taken into account. And finally, we have to know if the balance is based on a fiscal or a calendar year basis. First, we have to choose an energy unit. Then we have to choose the energy unit. It can be any energy unit. It can be British thermal units, ton of oil equivalents, joules, watt hours. The unit of account adopted by the IEA is the ton of oil equivalent, which is defined as 41.868 gigajoules. This quantity of energy is within a few percent equal to the net heat content of 1 ton of crude oil. The conversion of the IEA energy balance to any other energy units would be straightforward. The choice of the ton of oil equivalent is based on the history of the IEA creation after the first oil crisis. The difference between the net and the gross calorific value for each fuel is the latent heat of vaporization of the water produced during combustion of the fuel. This heat is lost and cannot be recovered. For coal and oil, the NCV is about 5% less than the gross. For most forms of natural gas and manufactured gases, the difference is approximately 10%, while for electricity and heat, there is no difference as they are not combusted. The use of net calorific values is consistent with the practice of the statistical offices of the European communities and the United Nations, and most importantly, it represents the useful energy. Generally, the IEA adopts country-specific, time-varying, and for some products, flow-dependent net calorific values supplied by national administrations for most products. For coal, the IEA has adopted specific factors supplied by the national administrations for the main categories of each quality of coal and for each flow or use. For natural gas and crude oil, specific factors have been used for production, imports, exports, and electricity generation based on consultations with experts from the national administrations. In the case of oil products, the IEA applies regional calorific values. So now we know how to convert combustible fuels in energy units, but what about nuclear, hydro, and other renewables? Why is it so important to compute this input, the primary energy equivalent? Because it is important to quantify the primary energy supply in order to calculate the total energy supply. A very important methodological choice is the definition of the primary energy equivalent for the electricity and heat produced from non-combustible sources such as nuclear, geothermal, solar, hydro, and wind. The information collected is generally the amount of heat and electricity produced, represented in the balance as an output of the transformation. Conventions are needed to compute the most appropriate corresponding primary energy input to the transformation, both in forms and in amount. For each of the following sources, that is nuclear, geothermal, solar, hydro, wind, tidal wave, ocean, and solar PV, there is a need to define the form of primary energy to be considered. For instance, in the case of hydro energy, a choice must be made between the kinetic energy of falling water in the turbines and the electricity produced. For nuclear energy, the choice is between the energy content of the nuclear fuel, the heat generated in the reactors, and the electricity produced in the nuclear reactor. For solar photovoltaic electricity, the choice is between the solar radiation received and the electricity produced. The principle adopted by the IEA is that the primary energy equivalent form should be the first energy form downstream in the production process for which multiple energy uses are practical. The application of this principle leads to the choice of the following primary energy forms: heat for nuclear, geothermal, and solar thermal, and electricity for hydro, wind, tidal wave, ocean, and solar photovoltaic. We have now identified the form of the energy input, but now we need to quantify it. There are essentially two methods that can be used to calculate the primary energy equivalent of these energy sources: the partial substitution method, which at the IEA we do not use anymore, and the physical energy content method. The physical energy content method uses the physical energy content of the primary energy source as the primary energy equivalent. As a consequence, there is an obvious link between the principles adopted in defining the primary energy forms of energy sources and the primary energy equivalent of these sources. For instance, In the case of nuclear electricity production, as heat is the primary energy form selected by the IEA, the primary energy equivalent is the quantity of heat generated in the reactors. In the absence of country-specific information, the IEA estimates the primary energy equivalent from the electricity generated by assuming an efficiency of 33%. This is derived as the average efficiency of nuclear power plants across Europe. For geothermal electricity, the primary energy equivalent is the quantity of heat, and a similar back calculation is used when the quantities of steam supplied to the plant are not measured. So assuming a thermal efficiency of 10%. This figure is only approximate and reflects the fact that the steam from geothermal sources is generally of low quality. If data for the steam input to geothermal power plants are available, then they are used directly as primary energy equivalent. Similarly, for solar thermal plants, the heat supply is back calculated assuming a 33% efficiency of conversion of heat into electricity, reflecting relatively low working temperatures. Although central receiver systems can reach higher temperatures and therefore higher efficiencies. In the case of hydro, wind, and solar PV, as electricity is the primary energy form selected, the primary energy equivalent is the physical energy content of the electricity generated in the plant, which amounts to assuming an efficiency of 100%. So when the primary energy form is heat, we have losses. Let us see a few examples to illustrate this concept. For wind, as we have an implied efficiency of 100%, so with 1000 TOE of electricity produced, the primary energy equivalent is 1000 TOE of wind. In the case of nuclear, as the implied efficiency is 33%, so for 1000 TOE of electricity produced from nuclear, the primary energy equivalent is around 3000 TOE of nuclear. In the case of geothermal electricity, as the efficiency is 10%, so for 1000 TOE of electricity produced from geothermal, we need 10,000 TOE of geothermal. For geothermal heat, the efficiency is 50%. So for 1000 TOE of heat produced, we need 2000 TOE of geothermal. Now, let us look again at the energy balance in tabular format and how to read it. These are the key elements to understand in an energy balance. We have three distinct blocks. The top part, which is the energy supply block, the middle part, which is the transformation and energy use part, and the last block, which is the final consumption. The last two blocks are what we refer to as demand. Only production of primary products are shown in the production row in order to avoid double counting. Secondary products are shown in the transformation block. That is why for oil products and electricity, the production cell is 0. The total energy supply row allows users to see the total amount of energy used and the relative contribution of each different source. Do you think this country is producing oil products? In the transformation block, there is a sign convention. Negative values represent an input and positive values represent an output. Transformation losses appear in the total column as negative values. In the total final consumption block, you have all the different sectors consuming fuels such as industry, transport, residential, and non-energy use. In this table shown in this slide, the energy balance is cut. That is why in the total final consumption, you are seeing only industry, but the table continues. As all fuels are reported in the same unit, then we are able to compute the total products column. In the transformation sector, the negative value in the total cell represents losses of the transformation process. I hope that this presentation has helped you understand some of the dynamism of the energy balances. Here are some key takeaways from the balances. Good energy balances are a compact source of energy information and is very convenient to use. However, a good energy balance requires good quality statistics, and not only in terms of data, but also calorific values. It also enables statisticians to run accurate checks of energy statistics, such as efficiencies, losses, etc. Also, they are the foundation for basic energy indicators, energy account, CO2 emissions estimates, and for modeling.
So now if you have any questions, please go ahead and ask us. I have been joined by my colleague Alexandre Bizel, who is an expert on energy balances as well. And we are happy to reply to your questions. I think there were a few ones already in the Q&A box and chat. So maybe Alex, you can.
Yeah, hi Zakia, hi everyone. Thanks for this presentation. There were a first question in the chat. Are the NCV ranges used here by the IEA the same as the one used for IPCC? So both the data published by IEA and IPCC are broadly consistent with the UNFCCC guidelines, the UNFCCC 2006 guidelines. In that respect, the carbon emission factors are mostly the same, and the NCV ranges, however, in the IEA, we are using NCVs that are varying by product and by time and by country for all the secondary products on the end of consumption side. I don't know exactly what are the NCVs used by the IPCC. So there are slight differences. The methodology is mostly the same. There are slight differences in the values used. For more details, please email so my colleagues that are working on emissions. So emissions@iea.org. But the methodology is broadly consistent between all those databases.
Yeah.
We had other questions like, can we calculate the energy intensity, the import dependence, self-sufficiency for one particular source of energy? So one product, I guess. Yes, we can. Zakia has shown you the self-sufficiency, for example, on biofuels only and in total products. So we can see that for one product, it can make sense to calculate the self-sufficiency. Yeah, as the products are really different and cannot be converted from one to the other. So we do publish in our indicators the self-sufficiency, for example, for coal products, for oil products. So regarding the self-sufficiency, yes. Regarding the energy intensity, we do not publish this by product. As one product may be used, different products may be used for several purposes. Let's say, for example, space heating. Some products may use mostly natural gas, or others may use electricity or oil. So calculating an overall energy intensity product by product might be misleading if a country tends to use one fuel or the others. So it depends if it's relevant or not, but for sure it can be calculated, yes. And the product definition is important here as well. We do publish here the detailed extended balances and the aggregated balances. So if you look at, let's say, diesel oil or the overall oil products, the figures may not be the same. So depends which product and if the products do make sense, but self-sufficiency for sure, yes, can be calculated.
Same for import dependency. We can calculate it with the energy balances as well. You can calculate, especially by product, it's interesting to see for a country to know on which product they are dependent on other countries.
And yeah, just to add something on the imports, you may have some countries that are, for instance, self-sufficient in terms of oil products in general, but they may export crude oil and then re-import refined oil products. So this is something interesting, and that can be seen if you look at the balances. Yeah, most of producing countries are in this case, for instance. So definitely useful to calculate this product by product.
Yeah. There's another question on for energy balance, can we use a mix of TOE and gigawatt hour? Well, this one, that the real advantage of an energy balance is having this this unique unit where you report all the products in the same unit, and then you can calculate your total energy balance. And so using a mix, no, I wouldn't do that, because that's one of the specificities of the energy balance. It's the common energy unit for the products. In our energy balance, usually we also report, for example, electricity. We give extra information at the in addition, you can have the electricity generation in gigawatt hour, because this is a value added, but within the energy balance itself, everything is usually in a common energy unit. So you have to choose between the two. I don't know, Alex.
Yeah, but then, yeah, for sure, the let's say the primary data, they are not necessarily coming in the unit used in the balances. The electricity generation is generally reported in kilowatt hours, gigawatt hours, but it's fine having at first as an input those gigawatt hours, but at some point convert everything to the same unit, so the calculations are done in a consistent way.
Yeah.
And then in the output tables, what also we publish here at the IEA, we have the output tables available in two different units.
Yeah.
So kilo or megaton oil equivalent and terajoules. So in the end, you can have the table available in whatever unit you want, and then look at the unit you want for specific product. But for instead of general reporting, the calculation method, we need to keep one single unit. Otherwise, things are really getting very complicated.
Yeah, I mean, otherwise you come back a bit to the commodity balances use. Yeah. I don't see any other questions. Give a few more seconds in case someone wants to drop. So we have a question in the chat box for African countries. How early in terms, years, timely series data on energy balances can we find? So for the moment, we have data published up to 2018, and we are currently working on the 2019 balances. We will have a release in April on some African countries for 2019, but not all of them, but you will have the full set for 2019 published in July, August, right?
Yes, exactly. We have 3 releases in the year. So we had the first release in February with limited number of countries with data until 2019. And next week we are releasing more countries, 90 countries in the world, and in July, the full coverage. So because the IEA is also publishing a country whenever all the data is ready, when you have something consistent in terms of supply and consumption. You may have some data on supply side available before, but here it was chosen on the IEA to publish whenever everything, whenever a country is complete. So
Yeah,
will be until 2019 for all countries next July.
exactly. And yeah, I think we are done with the balances part. So we will move now to CO2 emissions. Thanks, Alex, for joining me for this session. And now I'm being joined by my colleague Puya, who is an expert on CO2 emissions, and he will help with answering the CO2 emissions questions at the end. So I will share again my screen for the presentation. So now we will move and look at how do we move from energy balances to CO2 emissions estimations. So Africa has been a minor contributor to global greenhouse gas emissions during the age of industrialization. So as you can see here, energy-related CO2 emissions in Africa, it accounted for only 2% of global cumulative CO2 emissions from 1990 to 2018. So, and although Africa experiences important economic growth and energy demand growth, in the IEA stated policy scenario, its contribution to global energy-related CO2 emissions increases to just 3% of the total cumulative emissions by 2040. But having said this, Africa is in the front line when it comes to the effects of a changing climate on the energy sector. So beyond the impacts of cooling needs, climate change will also lead to increasing variability in generation outputs, notably hydropower. So planning and investment decisions for energy infrastructure needs need to be climate resilient. So again, here we will move to do some interactive questions on Menti. Sorry, I just lost this. So I will move to Menti website. Yeah. So this is the question. So again, please connect to www.menti.com and use the code 30 83 94 20. And the question is, if you have your energy balance calculated with a reasonable level of granularity, can you estimate your country's CO2 emissions from fuel combustion? So if you have your energy balance constructed with a reasonable level of detail, can you estimate your country's CO2 emissions from fuel combustion? You have three possible answers. Yes, you just multiply the total energy consumption by a fixed conversion factor provided by the IPCC. No, you need more information. Or yes, you can use the standard IPCC carbon intensity for each fossil fuel burned in the country. Give you some time to think about this. So most of you think yes, we can calculate, but some says we can just multiply the total consumption by a fixed factor. A bit more think that yes, you can use the standard IPCC carbon intensity for each fossil fuel burnt in the country. So now let's look at the correct answer. And the answer is yes, you can use the standard IPCC carbon intensity for each fossil fuel burned in the country. The first one, multiplying the total energy consumption, no, because we calculate CO2 emissions by products, so for coal, oil, and natural gas, and we have the standard IPCC carbon intensity by fossil fuel. We have another question. Which is the most CO2 emitting fuel per unit of energy? Here you have to order them from the most to the least emitting. So think about which one emits the most. Is it charcoal, LPG, fossil coal, or natural gas? Which one emits the most to the least? Here you have to classify them. So we have a few that are replying that excellent. So let's wait a bit more. So for the first one, indeed, you're right. The most emitting one is coal. The second one here, it's a tricky one because in our methodology, charcoal is classified as a biofuel. So it's a renewable product, and so we don't calculate CO2 emissions from charcoal. And then so this is quite tricky here for charcoal. In our data, we don't include charcoal for CO2 emissions calculation, and then it's LPG and natural gas. So now let's move to the presentation.
This chart represents the global CO2 emissions from fuel combustion. The share of the OECD countries in global emissions has decreased from over 55% to around 35% in less than 20 years. However, the global emissions have increased at a pace of around 2% per year, mostly driven by the emission growth in the non-OECD countries. The small blue line on top represents the sub-Saharan Africa emissions, excluding South Africa, and the orange line represents the other African countries. Despite the strong increase in the past 20 years, they correspond to only 4% of the global CO2 emissions, while representing about 15% of the global population. Credible and validated energy data are pivotal in providing high-quality emission estimations and greater confidence in the policy analysis. Access to comprehensive data enables detailed analysis of key sectors, fuels, and driving factors of emissions, both on a country-specific and global levels. This figure represents the sectoral share of CO2 emissions in the OECD, non-OECD, Africa, as well as a few African countries. The electricity and heat generation correspond to about 2/3 of global energy-related CO2 emissions from fuel combustion. Disaggregated data allows allocating the emissions associated with power generation to the end sectors and provide a more complete understanding of real drivers of CO2 emissions. The graph on the right represents the sectoral emissions after reallocation of power generation emissions to the end sectors. As you can see, in the OECD countries, buildings, transport, and industry are together responsible for about 85% of total emissions, while among the non-OECD, industry alone represents more than 50% of the total share. In the sub-Saharan Africa, however, transport remains the highest source of emissions, representing 50% of the total. Detailed emissions data enables populating matrix, which can be used to discuss the macroeconomic driving forces behind CO2 emissions and provide insightful input for effective energy and climate policymaking. The formula on the top is known as the Kaya identity, which allows decomposition of the total CO2 emissions into 4 macroeconomic factors: population, GDP per capita, total energy supply per GDP, and CO2 emissions per unit of total energy supply. As illustrated in the graph on the left, among the OECD, decreasing the energy intensity of the economy alongside lower carbon intensity of the energy mix have been driving the emissions down. On the other hand, among the non-OECD countries, increase in population, GDP per capita, and carbon intensity of the energy mix have been driving upwards trends in CO2 emissions, while the reduced energy intensity is slightly offsetting this increase. In Africa, the increase in population and wealth are the main drivers of emissions increase. Most of you are perhaps already familiar with the concept of greenhouse effect. CO2 alongside methane, N2O, water vapor, fluorinated gases, and ozone are known as greenhouse gases. The greenhouse effect refers to the circumstances where the short wavelengths of radiation from the sun pass through these gas molecules, but the longer wavelengths of the re-radiation from the Earth's surface are unable to pass through them. The trapping of the long wavelength radiation leads to more heating and a higher resulting global mean surface temperature. CO2 is the major contributor to global warming, and combustion of fossil fuels is the main source of global anthropogenic CO2 emissions. The burning of fossil fuels affects the concentration of CO2 in the atmosphere. Before the Industrial Revolution, the amount of CO2 in the atmosphere was about 288 ppm. We have now reached about 414 ppm, and we are on the way to doubling the amount of CO2 in the atmosphere by the end of this century. There's currently a strong scientific consensus globally regarding the role of emissions caused by the anthropogenic activities in increasing of global mean temperature. According to the IPCC special report of 1.5 degrees C, global temperature increases by the end of the century is likely to reach up to 5 degrees C above the pre-industrial levels if the current policy trends are continued and no significant action is taken. The United Nations Framework Convention on Climate Change, UNFCCC, is an international treaty adopted in 1992 to address climate change. Starting 1995, the parties to the convention have met annually to assess progress in dealing with climate change. In year 1997, the Kyoto Protocol was adopted and established legally binding obligations for the developed countries to reduce their greenhouse gas emissions. At the 21st Conference of the Parties, or COP21, in Paris, countries approved the new global climate change agreement, the famous Paris Agreement. The aim is to limit the global average temperature increase to well below 2 degrees C, with efforts to limit this further to 1.5 degrees C. The Paris Agreement was adopted in 2015 and came into force in 2016, with 187 countries ratifying it. In COP26, which is planned to be held in November, This year, countries are expected to communicate or update their national climate targets. The IPCC, with the help of IEA, has developed and refined an internationally agreed methodology for the calculation and reporting of national greenhouse gas emissions. The guidelines is called the 2006 IPCC Guidelines for National Greenhouse Gas Inventories Reporting, which is caused and used by the countries to report their emissions to UNFCCC. The IEA estimates of CO2 emissions are based on this credible international methodology. It's important to note that according to the IPCC guidelines, countries report their emissions under 5 different categories, as listed on the page. IEA deals with category 1, which corresponds to energy-related emissions only. Moreover, the energy-related emissions are divided in 3 subcategories under the guidelines. And the IEA estimates cover category 1A, which corresponds to the CO2 emissions resulting from fuel combustion of fuels only. However, as shown by the graph, energy is at the core of the greenhouse gas estimation, and the CO2 emissions from fuel combustion, which are covered by the IEA analysis, correspond to around 3/4 of total global greenhouse gas emissions. IEA CO2 estimates are based on globally recognized guidelines throughout the process. Our data collection process starts at the country level from national statistical or energy offices, where we collect energy data in physical units in the form of IEA energy statistics, which you are by now familiar with. From there, and based on the international recommendations for energy statistics as published by UNSD, and with the help of the net calorific values for various fuels, this information is put together in energy terms and forms the IEA energy balances, as it was discussed in detail earlier today by my colleague. Finally, and with the help of the default emission factors and methodology provided by the IPCC guidelines, IEA CO2 emissions are estimated. It's important to note that the IEA estimates of CO2 emissions from fuel combustion are a global database obtained following harmonized definitions and comparable methodologies across countries. However, they do not represent an official source for national greenhouse gas inventory submissions to UNFCCC. The IEA uses the simplest, the Tier 1 methodology to estimate CO2 emissions from fuel combustion based on the IPCC 2006 guidelines. Based on the Tier 1 method, the CO2 emissions from fuel combustion for a given fuel are calculated by multiplying the amount of fuel consumed in energy terms by the default fuel-specific emission factors provided in the IPCC guidelines. The computation follows the concept of conservation of carbon, which assumes that all carbon contained by the fuel burnt is oxidized and emits CO2. Emissions are then summed across all fuels and all sectors to obtain the national totals. It is also important to note that various fuels have different emission factors. For example, as you can see on the graph, combustion of a unit of a carbon-intense fuel such as a blast furnace gas corresponds to around 5 times of CO2 emissions compared to when the same amount of natural gas is combusted. And now to conclude, there is a scientific consensus regarding the role of anthropogenic CO2 emissions in increasing the greenhouse gas concentration in the atmosphere and the global warming. Effective emissions mitigation requires collaboration on a global level, and up-to-date and accurate information on greenhouse gas emissions are essential for effective climate policy making. And most importantly, the greenhouse gas emission estimates are only as good as the energy statistics, which underlines them.
So now if you have any questions, please go ahead. We have Puya with us who can answer questions. I saw that there was already. Hi, Puya.
Hello all.
So I saw there was already one question in the question and answer box, which you replied about bushfires, CO2 emissions.
Yes, for bushfires, the emissions are covered under the IPCC category 3, which is agriculture, forestry, and land use. And in real life, in nowadays, it also involves satellite monitoring data, carbon modeling, and that for estimating bushfire emissions.
Yeah. Please go ahead. Do not hesitate to write questions to us if you have any questions. We have time today. So everything was clear about energy balances. How do we use the data from the energy balances to calculate CO2 emissions using the IPCC guidelines and methodologies? We have.
Yes, so the question is, we have a question in the chat from Joshua, and it's about the sustainability of biomass, which is debatable in his opinion. And the question is, how is wood fuel and charcoal, which forms a big percentage of cooking fuel in most of sub-Saharan Africa, accounted for in the CO2 emissions? So this is obviously a debatable subject, and under the IPCC guidelines, as we discussed, under the energy category, the biofuel emissions are excluded. However, under category 3, which is again the agriculture, land use, and forestry category, we actually have to report the emissions which have been either absorbed by the various biosources or been emitted in various ways. So the difference is actually reported there, but not under the energy category. And in terms of sustainability of biofuel use, this is debatable. For example, when we define the SDG 7.21 figure for United Nations, which corresponds to share of renewable energy in total final consumption, right now, the use of charcoal and biofuel is actually included in this share, but excluded when it's used on sustainability. For example, as you mentioned, in sub-Saharan Africa, African countries, which is used for cooking for that. And since this is unsustainable, that share is actually excluded from the SDG 7.21 figure. So it's important to be able to differentiate between the sustainable and unsustainable use of biofuel and charcoal. I hope that answers your question, but let me know if you have any following up questions on that. I think we have another question on the macroeconomic drivers of the CO2 emissions, so the Kaya identity. Zaki, I don't know if you want to share the slide again. Might be easier to discuss it there.
Yeah, I'm Looking for it now. Wait. Share screen. Is it this one?
Yes, that's perfect.
Yeah.
So this formula on the top, it's called the Kaya identity. And this essentially helps us to disaggregate the CO2 emissions into 4 major macroeconomic factors which drive it. P is the population. GDP over P is essentially your economic growth. So it's the amount of gross domestic product per population. TES over GDP, it's essentially your energy intensity of the economy, which is total energy supply per unit of GDP. And CO2 over TES, it's the carbon intensity of the energy supply mix. And if you multiply this together, you can see that we can get to the total CO2 emission figure, which essentially was decomposed in these 4 major macroeconomic factors. Now, if you look at the figures on the graph in the OECD countries on the left, you can see that we have a very steep increase in the economic growth, which is GDP per population. And also alongside that, the population has been increasing steadily in the past 30 years, which is shown on the graph. However, on the other side, the energy intensity of the economy has been decreasing, and there has been also a slight decrease in the carbon intensity of the energy mix. And as such, these decreases in the carbon intensity and the energy intensity of the economy have offsetted the increase in the wealth and the population to a major point. And you can see that the total CO2 emissions have stayed relatively flat among the OECD countries. If you go to the next slide, I can explain Africa, which might be of more interest.
Wait.
Before that, so.
This one?
Yes, perfect. And this one is the same thing for Africa. And as you can see on the graph, population has had a sharp, steep increase. And there has been also an increase in the wealth. So GDP per population has also been increasing. On the other hand, the carbon intensity of the energy mix has been relatively flat. That shows the continuous dominance of the fossil fuel in the energy mix. And despite having a relative small amount of improvement in the energy intensity of the economy, this has only slightly offsetted the increase of the other factors. And as a result of that, you can see the steep increase in the CO2 emissions in the past 30 years in Africa. I hope that's clear, but I think it's very useful that with this Kaya decomposition, we can have a sort of an understanding of the major macroeconomic factors which is driving the emission trends in various parts of the world.
Thanks, Puya. I think you already answered the how do you account for CO2 emissions from kiln charcoal production? It's the same as what you said in agriculture, forestry.
Yes, and I mean, if in a general, also if one of the categories that we looked at for reporting emissions, the 5 categories, category 2 is industrial processes and product use, which under that category, you also report any emissions which is resulted of processes of producing, for example, cement, iron, because we also have emissions which are caused because of the chemical reaction that happens there. And those are all reported under category 2. And again, they're not covered by the IEA estimates, which covers the fuel combustion emissions only.
Yeah. Please, if you have more questions, we have a bit more time for questions.
So we have a question from Joshua. How do you account for lifestyle changes by humans towards reduction in CO2 emissions? That's an interesting question, Joshua. So we don't directly account for how lifestyle changes are impacting emissions, but obviously, as we change our lifestyle, that is going to impact how we consume energy in various sectors. For example, if you decide to use more bicycles or public transport or walking rather than driving, that is going to impact the energy consumed in the transport sector, and that is going to be translated in the emissions from the transport sector. So it's not something that directly we monitor for reporting emissions, but on the other hand, as we go towards hopefully aligning our lines more sustainably to achieve the Paris climate goals, it's going to be important to see how that impacts the underlying energy data and as a result, the emissions.
Yeah. No more questions? Well, then, if we don't have any more questions, we will move on to the exercise on energy balances and CO2 emissions. Thanks, Booya, for answering the questions with us. So I will share my screen now.
Thank you all.
Bye.
Bye-bye.
So I think you see the Excel sheet for the exercises. So the exercise, I hope you have been able to try, you got the time to try to practice this exercise. So I will just go with the solutions now. So again, here you are presented with an incomplete energy balance, and you had to fill the highlighted yellow cells. And the first question was, why does coal, electricity plants, and crude oil refinery are negative? And why is oil products refinery positive? So what is the question is, why is this cell here, C11, which is coal used in electricity plants, why is this negative? And the answer is, as you have seen in the presentation, in an energy balance in the transformation sector, there is a sign convention. So inputs are reported as a negative value. And for oil products, which is F12, so for oil products that is produced in refineries, this is a positive number because it is an output. So crude oil, which is the input, is with a negative sign, and the oil products, but the output, it's with a positive sign. The question 2 was, using the results from exercise 1, complete the simplified balance here for the year 2019 and use terajoules as unit. So here we know that in the exercise that we did yesterday, we had this balance of natural gas, terajoule, gross calorific values. So this is the table, and we are going to use that commodity balance and fill this energy balance. And here the unit, first thing you look at the unit, here it's in terajoule, but net calorific values. So when you are filling this, you have to be careful to adjust and convert the gross calorific value to the net calorific value, and the difference it's 10%, so you multiply by 0.9 here to adjust from gross to net. And here you just link to this one here. So production 2019, it's this number, and here it's equal to that number times 0.9. And you fill the whole column here like that, linking to the exercise 1 natural gas values. And for hydro and electricity generation, sorry. So here again, you have to fill it using the exercise 1 solution. So here the numbers, it's the same unit here, it's gigawatt in this exercise yesterday. Here is the table. So for coal in 2019, it's 688, and here you just report it for the different products in the different cells. And the total of electricity generation, it's just the sum of the different fuels. The next question is about and report hydro, solar PV, and wind. So for hydro, solar PV, and wind, you know the electricity generation. And again, here you apply the physical energy content method that says that for hydro, solar PV, and wind, we apply a 100% efficiency. So here, you know, but here it's in gigawatt, and the table above, it's in terajoule. And the conversion from gigawatt to terajoule, it's 3.6. So here, what you do is that because for hydro here, this is the input, you have to report it with a negative sign. You put negative minus 120 here, but you have to multiply by the conversion factor, which is 3.6 from gigawatt to terajoule, and you get it for hydro. For solar PV, it's the same. You take your electricity generation, you put the negative sign, and you multiply by the conversion factor. And same for wind. And now, given that we have filled all this, you are able to, given that you have summed all your electricity generation here, you're also able to calculate your electricity output here, which is just, it's the same value here, but converted into terajoule. Now for production. As we know, we have a 100% efficiency for electricity, for hydro. So here it's just this, and you apply your 100% efficiency here. And if it was nuclear, for example, if we had nuclear in this table here, you would have multiplied by 33%, which is the efficiency of nuclear power plants. So that was for this exercise. The question 3. Looking at the refinery transformation, do you see anything wrong? Why? Calculate the refinery efficiency and comment. So if we look at the refinery efficiency here, do you see anything wrong? So here, yes, your input is lower than your output, which leads to a positive number, which means that you're having gains. And we say that for your transformation, your output in energy terms cannot be higher than your input. And if you calculate the refinery efficiency, it's output divided by input, and here you have it above 100%. So what could be the reasons why you have an efficiency higher than 100%? So it means that either the oil products, the output here is wrongly reported, or your input is wrongly reported. So you have to query this with your data providers. It could be also for because of wrong calorific values used. It could be because of incomplete observations. It could be because of double counting. So there are many reasons why here we are ending with an efficiency above 100%. So the last question is about CO2 emissions. So calculate the CO2 emissions for total energy supply and electricity generation for each fuel and as a total. So here, what we said for CO2 emissions, you take the value and you multiply it by the emission factor. So here you are provided emission factors by product in ton of CO2 per terajoule, and you have your energy supply here for byproduct. And so the emissions for total energy supply, it's for coal, for example, you take your total supply in terajoule, you multiply by the emission factor. But here we are looking for kiloton of CO2. So here you have to divide by 1000 to get to the correct unit. And same for natural gas, you take your natural gas total supply, you multiply it by the emission factor, and you adjust the unit to get kiloton of CO2. And for the total of emissions, so you sum all the fossil fuels, so coal, oil, and natural gas. For electricity generation, it's the same here. So here we will take the amount of fuel that goes in the electricity plants, but given that here we had put the negative sign in the balance, here you have to readjust it. So you remove the negative sign, you multiply by the appropriate emission factor, for example, for coal, and then you divide by 1000, and same here, the total is the sum of the different fuels. The last question is calculate also the average electricity carbon intensity. So for this, to calculate this, you have to divide the emissions related to electricity plants by the electricity output. So for electricity CO2 emission intensity, you have to take this, your CO2 emissions from electricity generation, you divide it by the amount of electricity generation, and here you are looking for a gram of CO2 per kilowatt hour. So here, because here you were reporting in ton of CO2, you have to multiply by 1000. Here to, no, from gigawatt to, from kilowatt to gigawatt, you have to multiply by 1000. So here you adjust the unit. Same for natural gas. You take your electricity generation emissions from natural gas, you divide by the natural gas electricity generation, and you multiply by 1000. And the total here, you would take your total emissions from electricity generation divided by the total electricity generation times 1000. Again, here, for those who have not had the time to work on this exercise, I really recommend you to take some time and work on them. And if you want to send me your answer, the worksheet, I can take a look as well. And yeah, let me know if you have questions. It was a simple exercise, but I think it covered quite a few important notions to understand. I see we don't have any questions. So I think for today we have finished a bit earlier. which is, we have 20 minutes left, but when are you uploading today's lecture? So we try to do it in the afternoon. So, and we'll try to do it by the end of today, as soon as we can put it on YouTube. We will let you, we'll send you an email, or we usually put it on WhatsApp as well to inform you about it. Can you also update? Usually it's updated. Usually the YouTube playlist is updated as soon as we ordered. Maybe yesterday the assistant hasn't. I need to check, but I thought she had put it already on YouTube yesterday. But yeah, I mean, we put it as soon as it's done. We finish editing it on our side. Are there any additional homeworks where we can get more practice? I mean, we do have a few more. So if you are interested, we have from other trainings. Given the fact that we are doing it online, we try to put simple exercises so that it's also easy for you to do it. Usually when we do the trainings in a room together, we have a bit more exercises. So if you're interested, I could share a few other exercises. Just send me an email and I will see which other exercises I can take and share with you on the topics which you're interested in learning more. No problem. It's nice to see people motivated to practice more and learn more on the exercises. I think that's the best way to learn. It's by practicing and getting your hands dirty on the numbers. I think, can you forward us the Excel sheet with the class calculation? So you're interested in getting the solutions in Excel? Yes, please send me an email for those who want. Usually we have in the handbook that Arnaud had shared with you in the PDF, at the end of the PDF, you have also all these answers. So there's the questions and there's also the answers in the handbook that we shared with you by email. Can you please show us the solutions of yesterday's exercise 1 again? Sure. So this was yesterday's exercise. So it was asked to study the natural gas table. It was in million cubic meters, and here we provide you the gross calorific values and to calculate the weighted average calorific value here. So here, to calculate the calorific value, you do you take the production, you multiply by the calorific value plus the imports times the imports calorific value, and you divide it by the sum of the quantity, which is 9 production plus imports. So that would give you the calorific value here, and it's the same calculation for the years. So production times calorific value plus imports plus the calorific value of imports divided by the sum of the two quantities here. So that was the first question. Can you identify something wrong with the production gross calorific values? Yes. So here we see that the calorific value, it's constant over the years. So this is a bit weird. So this is something that can be due to because your data providers, they use the same calorific value for all the years, but these ideally calorific values, they have to be revised, and they do vary from one year to another. So you could discuss with your data providers, with the producer company, to know if they can provide you with more information on this. You could also try to develop a survey or a questionnaire specifically on this. And even sometimes data producers, they just report to you the quantities, but they don't report to you the underlying calorific values. So here you could put a mandate to oblige them to send you also that particular information. The question 2, it was about using the gross calorific value here, fill the data here in terajoules. So here you have data in million cubic meters. Here you have data, you want to calculate your data in energy unit. So here what you do is that you take your data in physical unit, you multiply it by your calorific value. In this case, we have calorific values only for production and imports, but not for the rest. So for the rest, you will apply the weighted average calorific value. So for all those except production and imports, you would apply the specific calorific values, but for all the rest, electricity plants, residential, you would apply the weighted average calorific values. So here, what do we see wrong? Do we see something strange here? So without adjusting, you see that here, no, the third question was calculating a verification indicator on statistical differences. So the check that we usually do is that we calculate the statistical difference over the total supply. And usually we expect it to be below 5%. Ah, sorry, I was not sharing my screen. Can you see it now? Can you see my screen now? Oh, I'm sorry, I was just talking and I didn't realize that I was not sharing the Excel sheet. So yes, we were saying that the indicator is for statistical difference divided by supply. And here we see something very strange. Now it's okay. Okay, sorry about this. Here we see that we have a huge statistical difference, which is very abnormal and something to be queried as well. So either here, when you have this kind of big statistical difference, you have to look at the different flows to see which one could be having an issue. So you would look really at the time series and see, here you can see very clearly that the electricity plants is going crazy in 2015. It's increasing a lot, but your supply has not increased that much. So there's a big difference between your demand and your supply. Then there was a question on electricity, using the natural gas and electricity generation data, calculate the electricity generation efficiency. So here you would take your electricity output in gigawatt hour for natural gas. You would divide it by your input of natural gas in electricity plants, but this is in terajoule, so you have to adjust it to, you convert it to the same unit, to gigawatt, and then you get your efficiency, which is output divided by input in the same energy unit. And here you see again that in 2015, something weird is happening. You have only 20%, which is very low. So here, it's not within expected efficiencies ranges, and most probably something is wrong in the electricity balance, and this is because of this problem here again. So how do we correct this? You would correct this by adjusting your efficiency. So normally, you know that the year before and the year after, the efficiency was 35%. So here you would apply a 35% efficiency. And here, so you would back calculate and apply a 35% efficiency here, and then here this would get fixed. That was it for me. Do you have other questions? Anyway, as I said, please, the best way to learn is to do the exercise, try to practice, and let me know if there are things that you are not able to do, and we can discuss. Otherwise, I think we are done for today. And I hope that you enjoyed this session on balances and CO2 emissions. So we will meet next Tuesday. So on Monday, there's no session, but on Tuesday, we will do the last of the 4 stat sessions. So we'll look at the energy prices and energy efficiency indicators. We will also do an exercise on both. So there will be 2 exercises on Tuesday, one on efficiency and one on prices. So please try to take a look beforehand. And yeah, I mean, whenever, if you have any questions, drop me an email or do not hesitate to contact us. I wish you all a good weekend and see you all next Tuesday. Bye-bye.